Of course, there are also high-dimensional time series problems, like imagine you're trying to control a robot that has 12 joints and a whole bunch of arms and bendy things. Well, if you want to know what will happen in the future if I control my robot in a particular way, you're trying to forecast the consequences of applying a force on this joint and this other force on that joint. And do you see how that's a multivariate time series problem? Okay. What if you're trying to predict the next frame in a video sequence? Very, very high dimensional sequence problem. Okay. Now, here's a problem a lot of people don't think about very often. Imagine you've got this type of data and you train, let's suppose you train on everything before the purple line. Actually, it's a magenta line. And you test on everything after the magenta line. How well do you think it will do? It depends. Yeah. Well, how good's your model? What does it do, right? But one of the fundamental assumptions of machine learning is that our data is independent and identically distributed. You've heard the term IID before, right? Oh, maybe not. Let me write it out. Independent, identically distributed. If we assume that all the samples in your training data are independent of each other, meaning the label in pattern 3 does not depend on the features in pattern 2. That's the independence thing. And which is not true in time series, by the way. And we also assume that they're identically distributed. What does that mean? Yeah. Give you an example of not identically distributed. We sample all the people in this room and measure their IQs, and then go off out into the world and try to predict the IQs of people at the mall. You see how that doesn't work very well, because there's a bias here. You are not random people at the mall. You are people in a machine learning graduate level class. Your brains are a little different than theirs. That was a nice way of saying you guys are smart. I'm complimenting you. Well, let's suppose you survey 1,000 men and find out that Star Wars and The Matrix are awesome movies, and then you go into a conference of feminists and you use your machine learning model to predict what movies they're going to like. How's it going to work out for you? I don't know if feminist was, I didn't mean of feminine persuasion type people. The point is you can't train on A and then test on B. It's just not going to work. You have to assume they're identically distributed, which means that the labels are related to the features in the same way between your training and your test data. Okay. Well, you see how in this case we have seen a whole bunch of values below this green line, and then we're testing on a whole bunch of values above the green line. And what will the model essentially do? It'll say, oh, I've never seen anything like unto these features before, therefore random prediction. Even though patterns like you see inside of this window are not unlike patterns that you might see inside of this window or that window, or right? So similar patterns might occur through time, but do you see that because the stock market is continuously increasing, the features of the recent past aren't really useful for predicting the near future. So what you going to do about it? How might one learn to predict the stock market given the fact that it's constantly increasing? Yeah.
Could you just normalize each window, take the average window?
Yeah, that'll do it. Essentially, so as it is, we're trying to do an extrapolation problem, right? We're trying to see what's off into the future. But imagine that our features were not just the last K patterns that we've seen, but suppose that they were all the current pattern that the ratio between what they were and the current pattern that we're seeing. Something like that. Meaning the current one is always going to have a ratio of 1 with itself, right? But the one just before it might be higher, might be lower, and the one before that might be higher, might be lower. If you always divide everything in the window by the last element in the window, now you've effectively normalized it so that the last one is always 1. And now do you see that it's more of an interpolation problem than an extrapolation problem? So just by doing a little clever pre-processing, we're now saying that, hey, this model, at least in normalized space, is kind of more doing a staying in the same domain type place. And then we're kind of trying to predict, what happens after this point. Well, have we ever seen anything like that before? Sure, kind of right here we did. And so therefore the model can say, this is kind of like that, therefore what happened right here is probably what's going to happen right there. And it turns out it didn't foresee that bump, and so it made a bad prediction, but could have worked out. Yeah.
The last pattern has there's more of the last pattern present in the gradient than there are in the previous several patterns.
Yeah, it could be analogous with it, I suppose.
The previous little interval because we divide everything.
Yeah, so with momentum, you're remembering stuff from the past in order to compute the gradient for the near future. So it's like it in that respect, but we're not merely summing in order to get what's in the future. We're predicting with a model. So in that respect, it's very different. Yeah.
When you're doing the error for prediction, it's like the first thing you predict is going to have some error, and then isn't that going to affect the second thing you predict also?
Yes. That's another important thing to realize about time is error exponentiates over time. I like to play this game where when I'm walking on a sidewalk, I like to close my eyes and count how many steps I can take before I accidentally step on the grass. You ever play that game? You were all in elementary school at one point, right? Okay, well, when you're terribly bored and you're walking down a sidewalk, try closing your eyes and see how many you can do. Well, if you just open your eyes for a picosecond, just barely open and close your eyes, just like that, every 10 steps or so, you can do it indefinitely. All you need is just that flash of momentary realization to know, oh, I'm drifting left or I'm drifting right. And if you've got that, you could walk down the sidewalk with your eyes closed 90% of the time and you'd be just fine. And when it's really, really cold outside, I actually do that to spare my eyes from the cold. If you keep your eyes just closed, how many of you think you can take 2 steps without falling off the side of the sidewalk? Everybody, right? How many of you think you can take 34 steps without falling off the side of the sidewalk? Pretty much nobody, no matter how straight the sidewalk is, because we all understand, at least somewhere in our minds, that the farther you go into the future, the more certain it is that your prediction is wrong. The future is chaotic and there's just no way. Therefore, don't ever try to predict the far future. It's a waste of your time. The very, very near future is all that matters. And sometimes people will measure sum squared error all the way far into the future because you want some meaningful number, right? You want to average over lots of test patterns. Well, what you end up getting is, suppose one of your models predicts like this, and one of your models predicts like this. Which of those models, magenta or cyan, is the better model? So it looks like magenta's better because it predicts the far future better, right? I'm going to claim it got lucky because it couldn't predict the immediate future, and yet it predicted the far future, right? So when you evaluate time series models, don't be deceived into thinking that predicting the far future is necessarily good. If you can't even predict the near future, you're already bad. So sum squared error, or mean squared error, root mean squared error, these metrics are very deceiving when it comes to anticipating time series data. Really, I want to say that cyan one, hey, it was pretty good for a while and it got the general trend and then it kind of got off as the problem grew exponentially more difficult. And so how do you actually measure better predictions from worse predictions? Well, it's a hard problem. Maybe you exponentially decay the weight of the difference. Maybe you only look two time steps ahead. Here's my mouse. Maybe you only measure sum squared error over a very tiny prediction window, in which case it's pretty clear the cyan one's better, right? There's a lot of things that could be said about it. I just want to make sure that you are aware of some of these challenges that occur. Yes? What time series data?
Just like after you measure the error of like the first one, let's say, then when you test to measure the error of the next one, you just replace that value instead of with your prediction with, since you already know those values, you just replace it with true values.
Yes.
So you still keep like the true values.
If you know the truth, don't use your prediction. That would be bad. And so, yeah, and a lot of times people aren't particular to specify in their evaluations whether they're doing that. Are they actually taking the truth and pulling it back into their model, or are they still using their own predictions? The difference is, if you're using your predictions, it's as though time had stopped right here and you're predicting far into the future. That's a very hard problem. Whereas if you're always predicting just one time step ahead, well, the world's worst model is going to fit almost perfectly to the data. It'll just be off by a tiny bit, right? Because you're only predicting one day ahead. So yeah, knowing the truth every time it comes up makes a huge difference in your accuracy, but it also means you can't have the foresight. Now that becomes really interesting when you think about intelligence. What is a human doing, right? I have to think, what actions am I going to do? And I have to foresee at least far enough to see the consequences of my actions so I can decide whether that's a good choice or not. Isn't that what we do all day long? That's kind of what the cerebral cortex of your brain is designed for, is recognizing patterns and anticipating their temporal outcomes. Well, in order to do that, you need some ability to forecast. And so the mind's really an amazing machine, particularly the more you start to realize what kind of a problem it's actually doing. Okay. All food for thought. Having said that, sliding window is one way to model temporal data. It's not the way we're going to do it. So that was just to get you thinking, and that's too easy. You guys can already do that. That's not a problem. Let's talk about another approach. The next method is recurrent models. I haven't really taught recurrent models yet, but think about it like this. There's kind of two models, not just one. And somewhere here in the middle, there's a bunch of values passing through, and then we're eventually going to make a prediction. Two models, right? Here's what makes a model recurrent, is if you take these intermediate values and you feed them back in. Now this is a recurrent model. Usually we've done feed-forward neural networks. When you suddenly have a recurrent neural network, or a network with connections that don't just feed forward into the next layer, what does that do? Well, it gives it the capability of learning values that it can remember and tell itself, which it can use to compute more values, which it can remember and tell itself, which it can use to finally predict what's coming out. Totally screws up backpropagation. Imagine trying to backpropagate error as it goes through these loops. You see what's going to happen? You've got a bit of a problem. But, and by totally screws up, I mean we've solved, there are solutions to this. But the capability of these things is really quite incredible. As long as there are recurrent connections that feed back in, this thing now has a memory. And so it can remember what it has seen. How big is the sliding window here? Well, in theory, it's kind of like it can decide. Like if it sees something that's meaningful or impactful in the past, it might decide to continue retaining that into its memory. and hold on to it for a long time. And then it sees a bunch of mundane things that it correctly predicted. It might not bother changing what's in its memory, and then it can utilize that in the future. So recurrent models are known to be very powerful. They're notoriously difficult to train. Although these days with LSTM models, we can do a lot better, and some really phenomenal results have been achieved with recurrent neural nets. The biggest problem with recurrent neural nets is they're notoriously hard to work with. Only really cutting-edge researchers seem to really be able to handle them and make them do anything, and in the industry, pretty much nobody touches them because they're scary and hard. So I don't think they're that scary and hard. I think I should make you do recurrent neural nets, but, well, we only have one semester, and I don't want to have to debug all your code. So I'm probably going to lecture about it, but not really go into much detail on them other than to say they're really powerful. Yeah.
Do you have a project on it?
Yeah, I can certainly make one if you're interested. Okay, cool. I like recurrent neural nets. I think they have huge potential. Yeah, I'm just going to put it on the back burner, and hopefully I can come back to it after we do the regression approach. So the third method for doing time series forecasting I will call regression. All right, I'll call it extrapolation. I will call it regression / extrapolation. Here's the idea of regression. Imagine you fit a model to the data that you have seen so far, and you continue that model into the future. Well, obviously you can predict, right? Wow, that was not a very straight line. The usual way people do regression and extrapolation is with linear models, because if you have a line, while it's going to ignore all the seasonal and all of the oscillating fluctuations in the model, it does a great job of predicting far into the future, except that it's ignoring all the finer details that you might be interested in. So linear extrapolation is kind of the standard for forecasting just because it works. Anytime you're doing financial analysis, you'll see lots of linear extrapolation. You won't see much recurrent models or sliding window. The recurrent models you won't see mostly because only neural net experts can handle them. Sliding window because, well, they just don't do a great job with financial data. And linear extrapolation seems to be the only thing that can handle it.